Okay, this is page 3 of the Chapter 1 review. The problem asks us to determine algebraically whether the following graphs are symmetrical to the x-axis, the y-axis, the origin, and or the line y equals x. So let's review what that means. Symmetry to the x-axis means that if you flip it over the x-axis, you'll end up with the same exact thing. Those are never a function because they won't pass that vertical line test, but they can still have that symmetry. The way that we check that is by making our y's into negative y and seeing if we end up back to where we started. This is x-axis symmetry. To see if things are symmetric to the y-axis, that's if we look at the graph, you flip it over the y-axis, and you end up back to where you started. Well, to figure that out, you make your x values into negative x. If I put in x, put in negative x, I should get the same thing. So if you get back to where you started, then you've got y-axis symmetry. For the origin, that happens when you look at your graph. You make your x's negative x's and your y's negative y's, and you get this awesome 180-degree rotation symmetry. X goes to negative x, y goes to negative y. If this is x, y, you're also going to have the point negative x, negative y. So that's the origin symmetry. And the line y equals x. Well, the line y equals x is this line. I know this isn't from Chapter 1, but symmetry about that line, we dealt with functions when they were inverses. For example, we've got the function 1 over x. Looks like this. If you flip it over that line, you get back to where you started. It's sort of a crazy function because it is its own inverse. So the line y equals x, to test that symmetry, well, you make x, all of your x's become y's, and all of your y's become x's. And again, if you get back to where you started, that means that the function is its own inverse. By reflecting over that line, you're back to what you have. So, here's the 4 sorts of symmetry that you can use. Let's put that off to the side. And let's start testing them. First thing, x-axis. Well, you make your y into negative y. Negative y equals the absolute value of 2x. Does it work? No. Let's go to y-axis. Here you say y equals the absolute value of 2 times negative x. Now the beauty of the absolute value is that when you take the absolute value of a negative number, it makes it positive. This just becomes y equals the absolute value of 2x. Yes, it is symmetric about the y-axis. You can also see that in the graph of the absolute value function. Third, we've got the origin. If I make our x's into negative x's and y's into negative y's, you end up with negative y equals the absolute value of 2 times negative x, which is, negative y equals the absolute value of 2x. No, not the same thing. And finally, the origin. Is this the same thing as x equals the absolute value of 2y? Nope, does not work. So this one only has symmetry about the y-axis. Let's look at the second problem. The second problem, if we make our x's into negative x's, let's start with the x-axis again. x's become negative, no, y's become negative y's. So you've got negative xy minus x squared equals 3. The answer is no, not the same. If you do it with the x's, that's going to be symmetry about the y-axis. Well, negative xy minus negative x squared, but negative x squared is just x squared, equals 3. Nope, not the same. Let's go to the origin. Negative x times negative y. Well, that'll just be positive xy. Two negatives make it a negative. Minus negative x squared is x squared equals 3. Oh, look, it is exactly the same. Yes, it is symmetric about the origin. There is one of your symmetries. If you change the x's and the y's, you end up with, for the y equals x, yx equals negative y squared. I'm sorry, that's not what it is. Yx minus y squared equals 3. Oh look, it does not work. No. Third problem, 1 over x. Let's check the x-axis first. Make your x into, no, your y into negative y. So negative y equals 1 over x, not the same. Let's do our y-axis. So y equals 1 over negative x. That is the same. Oh wait, definitely not. No, not the same. Your origin, well, negative y equals 1 over negative x, changing your x's and y's. If I multiply by a negative, this becomes y equals 1 over x. So, yes, it's not symmetric about the x-axis, it's not symmetric about the y-axis, but it is symmetric about the origin. Now let's check if we make our x, or swap our x's and our y's. Well, now we've got x equals 1 over y, but this is exactly the same as y equals 1 over x. We just multiply both sides by y and divide both sides by x. So, yes, this is symmetric about the line y equals x. Two types of symmetries in this one. We do have a problem that is symmetric. So, how do you tell if a function is even or odd? Well, even comes down to symmetric about the x-axis. No, not the x-axis, the y-axis. Odd is symmetric about the origin. As I said before, if it is symmetric about the x-axis, it's not going to be a function. It does not pass the vertical line test, therefore we don't really have a name for that. Just if it's symmetric about the y-axis or the origin. That is an even or an odd function. And I believe it comes from the fact that x squared and x to the 4th and x to the 6th are all even functions. Whereas the odd functions are x and x cubed and x to the 5th. But don't quote me on that because I'm not entirely sure. This has been Chapter 1, Page 2. Hope that it... Oh, Chapter 1, Page 3. Hope that it's helpful.